The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, everybody poops and everybody pees. We're talking with David Chu, a pediatric urological surgeon, about urine. Then we'll hear from his brother, Daniel Chu, who's a colorectal surgeon, about poop. And finally, we'll hear from IgNobel Prize winner Patricia Yang about her work studying the flow rate of mammal pee, and why all mammals pee and poop at the same rate. Welcome to Science for the People. I'm Bethany Brookshire, a writer with Science News and Society for Science and the Public. When people talk about the certainties of life, they often say the only certain things are death and taxes. But there are other things that come to all of us in time. For example, as the children's book says, everybody poops. And everybody pees. But how exactly does that happen? And what happens when it all goes to crap? To start us off with number one, I'm here with David Chu, a pediatric urological surgeon at the Children's Hospital of Philadelphia. David, thank you so much for being here.
It's a pleasure. Thank you for inviting me.
Now, first things first, starting with number one, why do we urinate?
Well, the body has multiple ways of getting rid of waste, and pooping is obviously one way, but peeing is another way, and it all starts up in the kidneys, the two beans that are kind of located side by side next to your belly button. The kidneys are, some might say, the most important organ in the body because they filter about a quarter of your total blood volume, and that's a lot of blood. So about 1 liter or a little bit more, depending on your body size, per minute. So it's a big type of filter for your bloodstream. And what it does is filters out kind of the waste products, filters out certain electrolytes from your blood, and converts that essentially into urine. And there's a whole host of little loops called nephrons in the kidney, which have multiple parts. Different parts of it focus on absorbing electrolytes, certain parts of it focus on absorbing amino acids, for instance. Certain parts of it focus on absorbing water back into your vascular system. But whatever remains gets dumped into the collecting part of the kidney, which then travels down the ureter and into your bladder, where, as we all know, you then pee it out. And
when you talk about filtering out waste products, what is considered waste in your blood? Like, what do you need to get out?
Well, there's a lot of small molecules in the blood, and a lot of blood actually gets reabsorbed. So, for instance, at the beginning of every nephron is a kind of a ball-like structure called a glomerulus. And what that does is it filters kind of the first initial stage. And certain things get trapped. For instance, protein should not get filtered through. But if there is protein found in the urine, that may be a sign that there is some injury to the glomerulus. That's just an example. But for instance, electrolytes, sodium ions, for instance, get filtered through. But a lot of that gets reabsorbed in the different parts of the nephron. And it kind of depends on how hydrated you are or dehydrated you are. It depends on kind of your blood pressure. I mean, the body has a lot of different mechanisms built in it that self-regulate. And so if, for instance, you're dehydrated, then the part of the nephron that reabsorbs water reabsorbs more water. And so therefore you produces more concentrated urine. But in the end, there are certain electrolytes that the body doesn't need or has excess of, and that gets put into the urine.
And you talked about kidneys doing the filtering. In my head, there's like a little screen in there, but that's obviously not what's happening. How does the filtration occur?
Yeah, it's kind of like a screen. I'm not a nephrologist per se, just someone who operates on the kidneys. But basic renal function, the glomerulus has different cells with kind of membranes across it. And these membranes, essentially, if they're normal, do everything kind of automatically. But if there are signs of injury at the glomerular level, then it's just like a screen. Bigger holes appear, and things such as protein, as I mentioned, can pass through, which shouldn't pass through if the membrane were intact.
And you mentioned that they filter out the waste, and the waste in some water kind of goes into the bladder. Once the urine is in the bladder, what happens? Like, how do we know that we've got to go?
That's a great question. So since I kind of focus on children, I'll tell you kind of how that changes from birth until we're an adult. So children, as we all know, they urinate frequently and kind of uncontrollably. And it isn't until kind of potty training age, when the bladder has grown enough in size, that we begin potty training. That essentially is teaching kids to hold on to their urine almost volitionally, and to go under some sort of better control. Part of that is due to the bladder increasing in size and be able to hold more. So normal bladder physiology is pretty complex, but in simple terms, there's two phases. There is a storage phase, which is when the bladder fills with urine that's made and filtered by the kidneys, and there's an emptying stage. So let's talk about the first part, the storage phase. The bladder is essentially a reservoir, and under normal circumstances, as it fills up, it is able to stretch kind of the properties of the bladder wall, the cells in the bladder, the muscle, the kind of inner lining layer. It has a viscoelasticity, which allows it to stretch and accommodate. It's kind of like blowing up a balloon in a way. And that property, that viscoelasticity property, allows it to stretch and accommodate in adults, up to 500 cc's without a huge increase in pressure inside the bladder. And that's important because you want to keep it a low pressure system to avoid injury upstream to the kidneys, for example. And a lot of this storage mechanism is under the control of the sympathetic nervous system, as well as probably the somatic nervous system. And, just to kind of give you a brief outline of the nervous systems in the bodies, there's part of the nervous system that we can control called the somatic system, and then the part of the nervous system that we can't control called the autonomic nervous system, which includes the sympathetic and parasympathetic nervous systems. Somatic is, kind of like you're raising an arm, or, lifting your leg up. The autonomic, controls a lot of things. Heart rate, for instance, controls kind of your bowel function, and similarly controls your bladder function. So the sympathetic nervous system is responsible for the storage phase of the bladder, and that essentially it relaxes the muscle of the bladder, such that it allows kind of this innate viscoelasticity property to work and to stretch without increase in pressure. Now, there's also a somatic part of the storage system. The somatic is leading, essentially, it's a nerve, the pudendal nerve, that leads to something called the external urinary sphincter. And this is linked strongly to pelvic floor muscles, such that, if you're ever taught to do Kegel exercises and you're squeezing down there, you're essentially kind of squeezing that external sphincter since it's part of the pelvic floor muscles. And so, for instance, if you are in a situation where you feel the urge to pee, but you're trying to hold it in and you squeeze down there, that's essentially where you're squeezing the external sphincter to prevent leakage. So that's all the storage phase. Now, when your bladder gets to a certain volume, there are certain nerves in the lining of the bladder that, when it gets stretched enough, sends a signal to the brain, to part of the pons of the brain, called the pontine micturition center, which then shoots signals back down to the bladder into the next phase, which is the voiding phase or emptying phase. Now, the emptying phase consists of two parts as well. One is the parasympathetic nervous system. That's what kind of causes the muscles around the bladder to squeeze, essentially to squeeze together to empty the bladder of urine. And there's also a nerve that leads to the sphincter, the somatic part of it, which essentially tells it to relax. So once the opening down below relaxes and then the muscle above around the bladder squeezes, then that's how the bladder is able to expel urine.
I love that the brain area is called the pontine micturition center because micturition just means to pee. And I guess calling it the Pontine Pee Center is just not professional sounding enough.
There's lots of nicknames for certain centers, but yes. That is probably the official, PC term for the center.
Now, you mentioned the whole Kegel exercises, and of course I started doing mine immediately. But this is what you do when you have to hold it. Can bad things happen if you hold your urine long enough?
Oh, absolutely. That's something that my mom always used to tell me growing up when I was a child, like, never hold your pee for too long, because things go bad. I don't know who told her. She didn't go to med school or anything, but it's true. too. And we see that frequently in kids, for instance. Kids who are taught and they're positively rewarded for not peeing in their diaper or not peeing in their underwear. But sometimes in kids, this can be overshot. And so then they pee once or twice a day, which is too rare a frequency. And part of the way they do that is by kind of squeezing down there when their bladder fills up to a normal volume that should trigger the brain to want to go pee, but they fight that. And you might see kids who kind of cross their legs or try to do other postures to kind of prevent or fight off that urge to pee, which unfortunately can lead to future bedwetting, can lead to incontinence, and lead to urinary tract infections, a whole host of bad outcomes. So in adults, it can also lead to impaired bladder function. Now, in adults, it's a little trickier because there may be other issues at play. For instance, in older men, benign prostatic enlargement obviously is a culprit in voiding difficulties. But taking all that aside, kind of fighting the urge to pee or peeing 1 to 3 times a day really isn't healthy. We encourage, especially in kids, they should pee every 2 to 3 hours. Normal adults should pee every 4 hours or so. And when you feel the urge, you go pee, and try not to fight it.
The pee must flow. Is that what you're telling me?
You must flow. Let it flow. That's right.
David, thank you so much for letting your urinary knowledge flow forth, as it were.
My pleasure.
We've linked to more information about David Chu at scienceforthepeople.ca. But we've only talked about number 1. What about number 2? To talk us through that, we're going to hear from a colorectal surgeon who also happens to be David Chu's brother. A colorectal surgeon and a urological surgeon. Their parents must be so proud. Stay tuned.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skeptic Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
To talk us through the number 2, I'm here with Dr. Daniel Chu, a colorectal surgeon and assistant professor in the Department of Gastrointestinal Surgery at the University of Alabama, Birmingham. Daniel, thank you so much for joining us.
Of course. Glad to be here.
Now, I want to start with a basic question. Why do we poop?
Yeah, so everyone has to poop. Everyone has to defecate, and it's part of the waste material that we have from digestion. So we all have to eat food, and what comes in has to come out somewhere.
And what is poop? We know it's kind of waste products, but what does that mean?
Yeah, so poop is really, as I described to patients, a combination of 2 main parts. So there's the undigested material, things such as fiber, and then there's water. And stool is really just a balance of those 2 products. And if we have too much water, we get diarrhea. If we don't have enough of the fiber or bulk to hold the water, then we get constipation. So those are kind of the both ends of the spectrum. And what we eat goes into our intestinal tract. Our body basically tries to absorb the nutrients that it can. And then what comes out is everything that it couldn't absorb.
Now, we know that poop goes, we know that poop doesn't go in. Food goes in. I hope poop doesn't go in. Food goes in to your mouth and down to your stomach, and then you absorb nutrients in the small intestine. But how then does digested food form poop? What exactly does it take mechanistically to form what we eventually evacuate?
Yeah, so what's interesting is that if you look in the intestinal tract, you eat the food that goes into your stomach as solid. Your stomach has acid, and it begins breaking down the food that you eat into smaller components, and it becomes actually very liquefied. as it works through your stomach and down to your small intestine, so that at the very end of your small intestine, which is something we call the terminal ileum, it's almost all liquid. And what happens at the very end of the small bowel is it connects to your large bowel, or your colon. And all that liquid, which is about 1 to 2 liters of liquid, gets into your colon, and your colon does the job of resorbing all that water. So that's when it becomes more of the solid poop that we tend to think of and that what most people have. So it's actually all liquid by the time it gets to the end of your small bowel. And once it enters your colon absorbs the water. You can almost think of it like a food processor sort of dehydrates what's there. And that's really when you get this more solid material. And so for people who are missing their colon, for instance, after surgery, those patients tend to have very liquid bowel movements, which is very typical. So mechanistically, that's really, in a sense, what happens is it's all liquid, and then you dehydrate or you reabsorb that water, and it becomes more solid. And then that can be that falls on a spectrum of whether it's too liquid or too solid.
And what is the spectrum?
Yeah, so the spectrum would be, if anyone who's had really, massive diarrhea, where it can be almost like pee, essentially. That's basically the most liquid form it could get. And then you have the solid form, where it's hard as a rock, what people describe, where people may be pooping once a week. That's basically constipation. And that stool, as some people can attest to, is just incredibly hard to get out and incredibly dense and has essentially almost dry sometimes.
And we talked about how the large intestine kind of resorbs all of this water from the kind of liquid that you have to create this this log, as it were. What happens once you have the log? Like, what occurs in the body to make us go?
Yeah, so that's a really good question. So it's actually much more sophisticated than what even I knew when I was in medical school. So the liquid kind of hits your right colon. Your right colon does most of the water absorption, and as it starts moving its way from the right colon all the way down to the rectum, which is the very end of your colon, it becomes obviously more solid. And what happens is that it builds up in the rectum. And the rectum is really a area that, in a sense, stores the stool, whether it's liquid or whether it's solid. And the rectum actually can blow up like a balloon. It has huge capacity to hold large amounts of stool. And that's a good thing, because you need that rectum to act like a balloon. Because if you didn't, you'd just be pooping all over yourself. And what happens is the rectum's on top of what we call the pelvic floor. That, in a sense, if you had to draw a picture, the rectum's like a single tube, and the pelvic floor is like a funnel. And you're basically putting this tube right through the funnel, except the funnel is a big piece of muscle that holds all of our innards up, so that it's not falling through our pelvis. And that pelvic floor is the key, because that pelvic floor senses when the rectum becomes full. And that's the sensation that we have when we have to poop. And when you have the sensation, most people have control and can hold it until it's kind of a socially appropriate time to go to the bathroom. But when that rectum fills with stool, you feel it, and then you have control, and then over your pelvic floor and the anus. And what's interesting, we don't know everything about this area, but it's incredibly sophisticated. But we have a lot of nerves in the anus and in the pelvic floor. And if I could just put it simply, the stool that's in the rectum eventually gets, and I'll put this in quotations, it's sampled by the top of the anus. So the anal canal can basically relax to a point where it can sample the contents from the rectum, whether it's stool or even whether it's gas. So when we all have to pass gas, a lot of us can feel the sensation. We know it's coming, so we can potentially control it, or even let it out and not let stool out. And so that's really all happening at the very end, where the pelvic floor, rectum, and anus is all kind of together. So this ability to sense and sample stool or gas then feeds back to our brains, and then we can have control of when to release and relax. So it's kind of a long-winded answer, but it's very fascinating and sophisticated mechanism in terms of how we defecate.
That's amazing. I had no idea that of course, I'm sure we all kind of feel the difference between, when you have to fart and when you have to poop, but I've never realized that the rectum can sense that really directly.
And the rectum, we really don't appreciate this until you remove the rectum. So patients, that we do surgeries on where we have to remove the rectum and reconnect things, we know the function's different. We tell patients you're gonna be, you're gonna be pooping more, and your poop actually could be more liquid. You might not have great control over it, but you should still feel when you're about to poop. And what's interesting is the nerves in the area too. In the colon, in the rectum, the nerves are what we call automatic nerves. They're nerves that you can't control with your mind. They're just always working kind of by themselves. But the pelvic floor and the very distal kind of part, some of the muscles around your anus, you do have control. So, if you're on as we say in medical school, when we pull medical students onto the front of the room and try to pimp them, their sphincter muscles tighten, right? So that's the part that you have control over. When you're frightened, you squeeze. When you're about to kind of basically fart in the classroom full of people, you can actually feel that sensation. You can actually hold it. You can squeeze a little bit. That's some control that you have voluntarily over your anus. So these nerves, though, in that area are very sophisticated and can really kind of determine whether or not you're, about to go solid or fart, basically. And so, if you ever think about it, you actually can tell a difference between the two. And, we always joke about the silent fart, on the school bus. But, those people knew it was coming. It didn't just happen. And they had some control over its release.
Well, now I'm sure that if we weren't thinking about it before, the next time we all have that feeling, we are all going to be thinking about it, because I know I will.
That's right, yeah. And what's interesting, too, is that, if you talk about the anus, and the anus is really the end, obviously, of the colon. So, again, it's just part of the long tube. And the anus itself, the way to think about it is that it's actually always slightly contracted. So, when we're walking around, this muscle that really is a circle around the anus is constantly contracted. And actually, so when we have to go, what we're doing is we're actually relaxing the muscles, and that's actually what lets things through. So when you're pooping, the same thing. When you're on the toilet and you're just relaxing, you can feel that relaxation, and that's when kind of the poop comes through that very end of the pelvic floor and the anus. What's interesting too is that there's actually another muscle that runs, and if I could draw a picture, it's like a sling that runs from kind of the front of your pelvis in a sling that wraps around your rectum, and it actually pulls and keeps the rectum at an angle, and it actually kind of pulls the tube in an angle so that the poop doesn't normally come out, and that keeps us continent. But ways to relax that sling or that angle is actually sitting. So that's part of the reason why it's really, if you ever tried, it's really hard to poop when you're standing. And in fact, pooping, you almost always have to stoop over and kind of on a toilet seat, and it's because that relaxes that angle so that you can actually have a straight tube and the poop can come out easier. So that's another kind of Mother Nature's clever design in terms of our mechanisms of defecating.
And you mentioned that the rectum is kind of like a balloon. It can accommodate a very large quantity. How much? Is there a limit?
So this, I wouldn't be able to tell you exactly the volume. I can tell you there is a limit because the rectum can get to a point where it holds so much stool that it can blow out, basically. So you can have colon perforations from stuff if it keeps building up in size. The rectum itself, if you think about the colon, can get over 10 centimeters in width. And so it can stretch the colon pretty far. So that's what we call compliance, or the ability of that wall to kind of stretch.
And you mentioned, there's all this relaxation that takes place. There's this sense of urgency, and then you gotta go. How often do most people go? Is there an average or a range?
So I would say that most people, go once a day. And but when you start going, we're talking like once a week, or 3 times a week. That's when you start thinking about issues of constipation. And there's a lot of different definitions, I guess, of when people would say that you have constipation. But basically, sometimes 3 times a week, 1 time a week. Those would be times when you start worrying about constipation.
And what is constipation? Like, we know it's a dried out stool. How does that happen?
So there's a couple of reasons for that. So most common reason is just purely dietary. So essentially, patients aren't having what I call, quote unquote, the perfect stool. And so, when I tell patients to work on their bowel habits, I say increase the fiber that you have to about 30 grams a day. And at the same time, you also need 60 ounces of water, 8 glasses of water a day. And that combination gives you what I think is the perfect ratio, and gives you stool that's not liquid and it's not pure solid. It's soft. It's right in the middle, so that it flows right out. And so that would be, about like a once a day kind of deal. So that's one reason. It's just the content of the stool itself is wrong. Now, that being said, then there are other kind of more nefarious reasons for why someone would have constipation and only poop once a week or once a month. Those could be more anatomical. So people who have problems at the pelvic floor, which is, the very end of the colon. Sometimes people will have floors that don't relax at all. Sometimes people have little, as I say, abnormalities of the rectum itself, things that kind of form extra cavities on the side of the rectum, something called a rectocele. These can be anatomic reasons why people can't completely evacuate their stool. And then other people have a condition where the colon itself doesn't work very well from a nervous system standpoint, and there's no propulsion of stool forward. And that's a more rare condition, but does affect many people, that potentially has a surgical solution for it, which is to take out their colon. So essentially, there's a couple different reasons why people have constipation. By far and large, the most common reason is just simply the stool and the habits that a patient would have. And then you have some more other medical, surgical reasons in which a specialist kind of has to deal with it.
So now that you've told me that there's such a thing as a perfect poop, you're holding up this image of, the perfect poop, and it's just one more thing for everyone to worry about. Are they pooping perfectly or not?
That's right. Yeah. So, and I would say, and I tell this all my folks too, whenever someone comes see us in our colorectal clinic, obviously something's usually going on with the colon, and with other problems, okay, not just constipation, stool, but sometimes there's problems with hemorrhoids, sometimes there's problems with pain in the anus, other issues like that. But the underlying, almost the first step we always take with all our patients for all of these constellation of problems is working on bowel habits, working on the diet. Because, we don't eat enough fiber here in the U.S. At all. And if you've ever recorded how much fiber you eat in a day, it's pretty abysmal. I'm in Alabama here. Meat is like a number one thing, and there's 0 grams of fiber in meat. And I tell patients, do you eat enough fiber? Patients always say, I do. I eat a bowl of oatmeal every day. Then I ask how many grams of fiber are in oatmeal. They don't know. They think it's everything. It's about 2 grams, 3 grams of fiber in a bowl of oatmeal. And you need about 30 grams of fiber a day is really what I tell my patients. So they have a long way to go. And so the perfect stool, getting that ratio is good not only for your colon and for bowel habits, but it can also affect other kind of disease processes too, and improve some of those symptoms. So it's a win-win basically across the board. You're not just helping your constipation. You can help any hemorrhoidal problems, any anal rectal problems. It's probably good for you also just from a cancer perspective in terms of laying off some of those red meats and just going back to really what kind of the people growing historically what we used to eat more of, which is fiber.
And you mentioned hemorrhoids. What are hemorrhoids exactly?
Yeah, so hemorrhoids. So that's like, oh boy, we could talk an hour on hemorrhoids. So hemorrhoids are essentially actually kind of cushioning of tissue that lines the anus at the very, very end. And one of these hemorrhoids, there's actually two levels of hemorrhoids, one called internal hemorrhoids and one called external hemorrhoids. The difference is basically internal hemorrhoids are higher up in the anus, and they're in an area where there are no nerves. And then the external hemorrhoids are below at the very end of the anus where there are nerves. Now, hemorrhoids are actually Mother Nature's clever design, and everyone has the tissue to form hemorrhoids. And if we look close enough, they actually swell up in everybody. So when we laugh, when we cough, when we sneeze, they all swell a little bit and actually contribute to our continence. Meaning, when we laugh, when we cough, it's not like we're blowing out poop every time we do that, or farting every time that we laugh, cough, or sneeze. So it actually helps hold in air, flatus, and stool. So it's a natural mechanism for continence. Now, it just happens, though, that for some people, usually older, the tissue gets more lax, and it gets bigger, and it forms these protrudes more. And it gets to a point where it can protrude so much that it can potentially droop out through the bottom. And that's when people really start noticing things, because they're wiping and they feel a lump on their bottom. And those could be hemorrhoids. So they're actually Mother Nature's natural design to keep us continent. It just gets bigger and looser in certain individuals. And in certain individuals, it gets to a point where it's so big that it can basically sometimes, for example, be cut by a ball of hard stool. So again, people who get constipated have hard stool. These stool balls can basically cut the tissue, and it's paper thin. And when they cut it, it's like a paper cut, and it bleeds like a mother, and it's bright red blood. People get really scared. It fills up the toilet bowl because it's diluting out into that whole water. And then and then they get what we call bleeding from hemorrhoids, which is probably the number one issue with hemorrhoids, and why people come in to see us is they start seeing bleeding after bowel movements. So that's sort of a short description of hemorrhoids. So we all have them. They're actually, in a sense, natural for us to keep continence, but they can become bigger and become more kind of pathologic and cause problems like bleeding, and that's usually when we get to see them.
Now we've kind of talked about the hard matter, as it were. So can we switch a little bit over to the soft matter? What causes diarrhea?
So good question. So kind of similar to the flip side of hard stool, again, dietary function plays a big role in terms of the consistency of the stool. And so probably one of the things that we say when someone has very loose stool is to ask about, well, how much water are you drinking? And then how much fiber are you eating? So the same story again. And sometimes a lot of these people, we don't have enough fiber. So we bulk up the stool, meaning we add fiber to their diet. And this is the bulk. This is the part that can never be resorbed by your colon. So it always stays there and it holds the water, draws in water essentially, and then can bulk up and kind of reduce the amount of loose stools that happen. So that's probably one of the common reasons for diarrhea. The other reasons, though, for diarrhea are usually what everyone can remember when you get a GI bug, for instance. And so what happens there is that essentially the colon basically either doesn't do a good job resorbing the water because of the disease infection, or it actually can secrete fluid backwards. So it's almost backwards. It secretes fluid into the lumen of your colon. So it adds water into the lumen. And then that can contribute to just huge amounts of diarrhea.
Now, if you have time, I'd like to take a side trip into flatulence. The best kind of side trip. Why do we fart?
Yeah, so part of the reasons when we talk to a lot of the reasons, a lot of the gas that's produced in our intestines is actually from air that's swallowed. So that's actually something that is kind of surprises people. So yes, the bacteria in our gut can produce some amount of gas that can contribute, but a lot of it actually just has to do with what we swallow from our mouth that works its way all the way down through the anus, essentially. And so that's the number one, I would say, reason for why we have flatus. And then number two would just simply be the bacteria, and we have tons of bacteria living in our colon and trillions of it, and it's a huge amount of living organisms that can potentially form gas from the different kind of foods that we might eat. But when we do surgery on patients for the colon and rectum, and we reconnect people, one of the first things that we always ask for every day when we see patients post-operatively is whether or not they pass any gas. Not so much are you passing any stool. We actually care more about gas than stool because we know that the gas largely comes from the mouth. So if someone's passing gas, it means that their GI tract is open. It's working. They're passing gas from the mouth all the way down through to the bottom end. So for us, gas is very important. We don't care so much about stool because the colon, again, can, even if you disconnect everyone's colons and just leave a little blind end there, that colon will still produce stuff. It still produces mucus. So people can still have bowel movements, even if they're completely disconnected from the rest of their intestinal tract.
Now, you mentioned a little earlier that, some farts are the silent but deadly variety that causes school bus havoc. What makes some farts more smelly than others?
Yeah, so that's interesting. So I won't be able to tell you exactly why it is, except that that some of it has to do with some of it has to do with the foods that we eat, and so things like meat sometimes have smellier farts. So that may just have to do with the way that the bacteria processes some of the foods that make it to the colon.
And why are some farts, so that, you mentioned the silent but deadly. Some farts make noise and others don't. What causes farting noises?
Yeah, so that just has to do with the apposition or the kind of the way that the anus is. The anus is normally closed when you look at it. And so, because it's constantly contracted. And so it's the degree of relaxation. And it's kind of just like, those tricks you can use where you squirt water through the cup of your hands in the swimming pool, and you can squirt water out. You can also make farting noises that way. It's essentially the tissue, the air moving through kind of opposed tissue that essentially, when you look at it closely, can flap and causes that noise. So silent farts, you can, if you stretch out we did this at school, let's just remember, you stretch out your butt, pin one side down on a chair, move it way over to the other side, stretch out your anus a little bit, it can be a silent fart. Keep it together. It's like blowing your cheeks together. It can be very noisy.
So noisy farts are from uptight people.
Never thought about it that way, but entirely possible.
Well, Daniel, thank you so much for this fascinating fecal focus.
Absolutely. My pleasure.
I am so thrilled to finally meet someone with whom I can spend an hour talking about hemorrhoids, so I hope you're free later.
Absolutely, yes. You can reach me anytime.
We've linked to more information about Daniel Chu, as well as some scientific writing about feces and farts at scienceforthepeople.ca. Next up, we're talking with someone who does research that might be called crappy. It might piss some people off, but it's good. It's solid. There's no floaters here. We'll hear from Patricia Yang about her work calculating how long it takes your average mammal to pee and poop. Stay tuned for more science and for my wealth of poop puns.
Every week on Science for the People, we take the latest in scientific progress and relate it to people, our friends, our families, our communities, and our society. And we give researchers, authors, and journalists the time to talk in depth about what matters to them. If you love science but aren't satisfied with sound bites, join us again next week for Science for the People on your local radio station or anytime online at scienceforthepeople.ca.
Welcome back. I'm here with Patricia Yang, a mechanical engineer at Georgia Tech University in Atlanta. Patricia is a graduate student in the lab of Dr. David Chu and is most well known for her 2014 paper, Duration of Urination Does Not Change with Body Size. With a paper like that as number 1, is it any wonder that she tackled number 2? Her latest paper out this year is called The Hydrodynamics of Defecation. Patricia, thank you so much for joining us.
Hello, nice to be here.
Now, you are a mechanical engineer. Why are you studying pee and poop?
They are actually fluid mechanics. If you can imagine, they are waters. We mostly focus on waters not inside our body, like splashes, air conditions, but actually the fluid inside our body that keep us body function are important, and they are fluid mechanics.
And why is it important to study how long it takes animals to pee and poo?
How long it takes, the time, the duration of it is actually, I would say, the comic version of this study. But more important is we want to have a easy, quick, non-invasive test for bladder health or gut health.
So if an animal takes a longer or shorter time to pee, for example, it might indicate something about their health?
Yes. For example, people might notice there's a wide range of my study in time, like I say 21 plus minus 13 or 12 plus minus 7. So if you're 22 seconds instead of 21, you're fine. But if you're like more than a minute, then probably you should see a doctor.
Now, for your first paper on urination, you got video of different kinds of mammals peeing. Can you give me a range of some of the species that you got video of?
Oh, yeah. So actually, people thought I took all the videos, but most of the videos are from YouTube.
And what was that search function like?
It's simple, right? Just do. You will be surprised. There are actually tons of animal peeing video in YouTube.
I don't say that I'm surprised. I just
really?
It seems a little adult.
Okay, maybe. Anyway, so we just search elephant pee or rhino pee, rhino urine, or dog, any mammals you could think of at zoo. You just search a name, pretty much you can get all of them.
And when you had all of your species, you ended up actually dividing your mammals into small mammals below 3 kilograms and larger ones that went up to about 8,000 kilograms. Why did you draw that dividing line?
So I actually, previously I said I got most of the videos from YouTube, right? But then some of the animals, they don't have it on YouTube. Say, bats, rats, mice, these common lab animals, or some very, very big animal, and we want to know the details, say elephants or goats. So I actually filmed them at zoo and on campus. So we figured out for small animals, like I said the line for 3 kilograms, they are actually doing these very high-speed droplets. And you can only see it when you film it with high-speed camera.
And larger mammals produce urine in kind of a jet or a stream. Why do small mammals have this high-speed droplet style?
So the reason why these small animals, they do droplets is because they're, the name is called urethra, but you might be easier to understand if I say that's pee-pee pipe. This is the pipe from bladder to when it comes out. So this pipe, for the smaller animal, they are too narrow, so they have very high resistance from viscosity and surface tension. This resistance divides the stream into droplets, and the small animals like rats, mice, and bats, they actually squeeze out these droplets.
So because there's too much resistance, it can't form a full jet?
Yes. But for larger animals, they don't have this problem anymore. Like for smaller animals, I say 3 kilograms, like small cat to lions to elephant, of course, their urethra is way wider compared to small rats. So the surface tension or the viscosity are not that important.
Now, you ended up creating a model for the duration of urination. How did you do it? Like, what factors are really important for how long it takes to pee?
The most important factors are the dimensions of urethra, including the length, which is the height of urethra, and the width of urethra. We found that for larger animals, definitely have wider urethra, and the width of urethra dictates how big the orifice is. So there's more flow, of course, but also the height of urethra that dictate how much acceleration from gravity it could get. So the taller the urethra, you can get more acceleration from gravity.
So does this mean there's a sex difference as well? Because, females have different urethras, and of course they also pee at a slightly different angle compared to male mammals who of course have this penis that's hanging.
Yes, actually that is something I'm trying to figure out right now, is how we didn't see a very obvious gender difference in timing. But we are collaborating with a urologist in Japan. And he actually he did a survey at like a train station to 2,000 Japanese people about their timing, their urination time, and their gender, their age, everything. So the gender difference actually is obvious for human being, for males and females, but not that obvious for other animals, because humans are animals that have urethra, and let's say human females, they have divided channel, say vagina and urethra. But this division is not exist for other mammals. Say for rabbits or cats, the bladder are actually connected with vagina and go through the same channel.
Really? I didn't know that.
Yeah, that's gonna be my next study, my next paper. So it showed if you count the effective height, including the part that's connected to the vagina, the length of this affected urine path is actually similar to that of males, but it's not happening for humans. So you will see obvious the difference in human being, but not animal data.
And to do this, one of your collaborators actually timed people peeing in train stations.
They gave out stopwatches.
I want to hear all about that study when it comes out.
Oh, so it's actually a collaboration after we got interview from NHK, and they found this clips about what we're doing at zoo and on campus, and this medical doctor spread out a survey and kind of make it interesting for people to join. So they found the urination time is actually correlated with the human age and the gender. So if, say, for elder people, they actually pee longer because the degradation of bladder muscle. But for let's see, if I can remember correctly, males are actually pee a little bit faster than females.
That is awesome.
If I remember correctly, yes.
And your paper actually did come up with a final duration of peeing for large mammals and small mammals. What are the numbers?
They are, for large animals, they are 21 plus minus 30 seconds.
So that can be up to almost a minute.
Yes, and this is exactly the average timing, average second from that 2000 survey.
And what about small mammals?
For small mammals, it should be less than 1 second, but we only have 3 animals. Bats, rats, and mice. So we are not very conclusive at this point, but we believe it will be less than 1 second.
Now, moving on to more solid matter, as it were. Once you did urine, you moved on to poop and took video of animals defecating. What animals did you end up filming at the zoo?
So elephants are the best. They never been shy. So we can film them, and they have regular peeing and pooping time. So we can predict and go there with schedule and film them expected in 2 hours. But for other animals, they might have camera shy while pooping. So we have elephants, pandas, warthogs, and dogs that we can get a close up of defecating.
And why did you pick pandas?
Because they are just not shy of camera, and they usually poop at the position that some of the animals, when they poop, they hide, so we won't get the shot of their butt. But the pandas don't do that, so we can get perfect angle of their butt, and their poop. And
when you filmed dogs, you actually filmed at dog parks. How did that go over? Did the dog owners give you funny looks?
So the dog owners is actually one of the author. It's Candace's dog.
Oh, so you took a specific dog to the dog park?
Yeah, Candace is one of the best students I have ever had. So you couldn't believe this, but all the videos and photos on this close-up shot took her 1 semester staying at zoo every weekend.
Wow. She was at the zoo every weekend filming people, animals pooping.
Animals poop, yeah. And she could only get 3 of them, elephants, warthogs, and pandas. And I said, no, we need 4 for the paper. We need 4. And she's like, okay, I will try my own dog. And then after a weekend, she got the shot.
And you ended up dividing the poop into sinkers and floaters. What's the difference between sinkers and floaters?
So we collect a bunch, pretty much all feces from all mammals at Zoo Atlanta, and we start to test over the properties, including density or viscosity. We can discuss later. But for density, we just test over with a scoop of the volume we know and test over the density of it. We figure out for herbivores, the poop are actually just formed by haze, fibers, and a little bit amount of stones there. No, there's no stone, just fibers. So it's lighter than water. And for sinkers, they are from carnivores like lions, cats, and the poops there in form of hairs, bones, and stones. So they actually are way denser than water.
And as well as measuring the density, you actually looked at the rheology of the feces. What is rheology?
Rheology is this fancy term in academic, but it really means how sticky it is, how viscous it is.
So how slimy. Basically.
Yes. How would you feel when you step on dog feces?
And how do you measure that other than, stepping on dog poop on purpose?
There's actually a very professional equipment called rheometer, which is measuring rheology of a specific material. And how it works is actually more like a blender. So it rotates, it blends the material. Say I put feces in, okay, it blends the feces at a specific rate I want and measure how much resistance during that rate.
So it's like a gigantic blender that just measures the blending.
Yeah, measures at different rates though. So you have, say, 5 speed, and you measure if when you increase the speed, when you blend it faster, will the material be more sticky, or more watery?
And you also found that, like the constant rate of urination, mammals have a constant rate of defecation, right? What were the numbers?
It's 13 seconds plus minus 7 seconds.
And what I found really interesting about this paper is that a lot of this pooping rate has to do with mucus, which is something I'd never realized before. What is the role of mucus here?
Mucus is a small, transparent, liquidy fluid everywhere in the body, like say in tears is more like water, so not mucus, but more like say in your throat all the way to your gut, or maybe when you got cold, your nasal fluid, they are mucus. So it's a little bit sticky but transparent, and the thickness of this liquid is actually the key of defecation. It helps lubricate the process. The time when I measured the viscosity using the blender of the feces, I figured out actually it's no way for animal to defecate this amount of material in 13 seconds. Because the material is more like solid. But because of the mucus, that transparent fluid coating outside the surface of feces in between, so the in between feces and the gut, like the rectum. So that's the fluid that lubricates the whole process.
So basically, poop is way too sticky and solid to come out on its own. We need something to make it slide.
Yes, and that would be it actually indicate if you have constipation, probably it's because you don't have enough mucus.
And what about with diarrhea? Does that affect your model as well?
Yeah, so we just said, we have a bunch of data on property of feces. So we can test over dry feces and watery feces. So for diarrhea, we just assume a very extreme case that you are defecating water. And in that case, you probably don't need any pushing force from the body, but just need gravity. And the whole matter could come out in less than 1 second. Yeah.
Yikes.
Yeah. So yes, you probably have to see a doctor too.
And you did this model of defecation in animals at the zoo. You looked at the rheological measurements of all of these animals and lots of video at the dog park. Does this model of pooping apply to people? I think so, because the main feature of my study is I do with a lot of animals that cross wide range of body size. And I believe humans are in between. Say,
from dogs to elephant. And the feature is that no matter if that's duration of urination or defecation, the time does not change with body size, which means the time of defecation, we are all the same.
So if that's the case, then why do we spend so much time in the bathroom?
Okay, let me tell you how I time the duration. People ask this question a lot. So when I count the time, I look at animals' butt very, very carefully. And when I start the timing, when I see the first piece of feces comes out. But for human being, you have iPod there, you have newspaper, you have everything. And I didn't get a chance to look at very closely when the first piece came out.
So there's a lot of stuff going on before the pooping in people.
Yes, and you should not count newspaper time.
And this doesn't apply to all mammals because not all mammals poop in logs, right? What about animals that poop in pellets?
Yeah, so in this first paper of poop, we only talk about the mammals that defecate logs in different, say, 2 pieces or more than at most 4 pieces of logs. And there are some animals, say rats, rabbits, rodents, rabbits, and ruminants. They actually defecate with single pellets or a bag of pellets feces. So for these animals, apparently they are different. The process is different. They do have mucus outside, but it's more like how the feces breaks in the body and how the sepia form.
And has this really changed how you think about urination and defecation? Like, has this changed your life?
Oh yeah. So, you might. So in all our research meeting over this. So I'm 5th year, going to be 6th year graduate student. So during the past 5 years, all the meetings are what we have found and what I feel. And no, that's not what I had last night.
So you're constantly comparing the video to your own personal experiences?
Yeah, because as a scientist, if you want to convince other people, you gotta convince yourself or your team first, right? And say I propose this idea of mucus, and people think about it like my advisor, and then the other day he talking to me that, but I didn't see mucus. Where is the mucus? You need to have visualization of it.
So what you're telling me is next time we all use the bathroom, we need to look for the mucus.
Actually, mucus is very, very thin, like about the thinness of your hair. So you can only get that shininess if you have fresh feces less than 30 seconds.
Okay, so look quickly.
Yeah, and probably that'd be easier if you have a dog, that'd be easier. Just observe the poop from your pet.
And should we report to you if we find good mucus?
Yeah, that'd be great. Actually, I got a lot of self-report data on urination time after my first publication.
Hey, people just want to help science, man.
I feel honored, and thank you for everyone.
Well, thank you very much for coming on the show.
Thank you.
If you'd like to learn more about Patricia Yang's fabulous work, we've linked to her papers and her Twitter feed at scienceforthepeople.ca. You'll also find links to Twitter, Facebook, and iTunes, where you can listen to past episodes, subscribe to the show, or leave us a review that hopefully does not stink. You can also find our Patreon page, where you can support our intrepid band of podcasters with a monthly donation. Thanks for listening, and we'll see you next week on Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skeptic Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by Science News writer Bethany Brookshire and me, Rochelle Saunders.